Today, we're diving into a material that's, well, genuinely a supermetal. We're talking about something so tough and so important that you can find it in jet engines and inside the human body. But, its greatest strength is also its biggest weakness. We're going to break down a pretty revolutionary new way of working with this stuff, a technique that's finally taming this beast of a metal. And that's really the core of the problem, right? You have this one material that is perfect for two completely different worlds: the high-stress, high-performance world of aerospace and the delicate, life-saving world of medicine. But the very thing that makes it so strong also makes it an absolute nightmare to shape and manufacture. All right, so let's properly introduce the hero of our story and the huge challenge that comes along with it.
The material's full name is titanium-6 aluminum-4 vanadium. Yeah, it's a mouthful. So everyone just calls it T6Al4V. And its resume is frankly incredible. It's ridiculously strong for how light it is, and it basically doesn't corrode. This is the stuff you use when things absolutely cannot, under any circumstances, fail.
And this isn't just some fancy material stuck in a lab. It's already out there all around us. It's in the critical parts holding airplanes together. It's used to literally rebuild people. We're talking hip replacements, plates to set bones, you name it. So you can see why getting this right really, really matters. So here's the big hurdle. The old school ways of shaping metal, like using giant custom molds to stamp out parts, are super expensive and take forever. They're fine if you need to make 1,000,000 of the exact same thing, but they're terrible if you need a one-of-a-kind medical implant for a specific patient or a unique prototype for a new jet. We just needed a smarter way to do it. And of course, that smarter way now exists. So let's get into the really cool part, the innovative solution that researchers have been perfecting, a process that could unlock the true potential of this amazing metal. It's a technique called incremental sheet forming, or ISF for short. Now, the magic words here are die less. This means you don't need a huge, expensive mold. Instead, ISF uses a simple, little rounded tool. The best way to picture it is like a robotic potter's wheel, but for super strong metal. It just slowly and precisely pushes a flat sheet into a complex 3D shape, one tiny little push at a time. The whole thing is wonderfully digital. It starts with a 3D model on a computer. That software then creates a super precise path for the tool to follow. You clamp a flat sheet of the titanium alloy into place, and then a CNC machine, which is just a computer-controlled robot, takes over, following those instructions perfectly, shaping the part bit by bit. Okay, so having a great process is one thing, but with a material as tough as this titanium alloy, you need the absolute perfect recipe. If you get the settings wrong, if you push too hard or move too fast, you can totally ruin the part or even break the machine. So researchers had to figure out the absolute best way to get it done. So their mission, essentially, was to find that perfect sweet spot. They needed to figure out how to get the most accurate shape possible, which they measured by how steep they could make the part's sides, called the wall angle, while using the absolute minimum amount of force. It's a classic engineering puzzle. To find that sweet spot, they basically had 3 main dials they could turn up or down. First, how fast the tool spins. Second, how deep it pushes into the metal with each little step. And third, how fast the tool moves across the sheet. They just tried a whole bunch of different combinations to see what would happen. And the results? Well, they were fascinating. Some of it was what you'd expect, but one of their findings was totally counterintuitive. Let's break down what they discovered. Okay, so the first finding was no big surprise. The deeper the tool pushes with each pass, the more force you need. I mean, that makes perfect sense, right? You're trying to move more metal at once, so of course it's going to fight back a lot harder. But this is where it gets really interesting. You would think that spinning the tool faster would take more force, right? Nope. The exact opposite happened. A faster tool speed actually lowered the force needed to shape the metal. And the reason is just brilliant: friction. Spinning the tool really fast created this tiny pocket of intense heat right where the tool meets the metal. That heat softened the titanium just enough to make it easier to bend. They were using the process to trick the metal into cooperating. And this quote from the study pretty much sums up the double win here. Not only did spinning the tool faster mean they could use less force, but it also helped them create a better, more accurate part with a steeper wall angle. It was the best of both worlds. So after all of this meticulous testing and number crunching, what did they actually figure out? Let's look at the perfect recipe they landed on and what it really means for how we make things in the future. So after they fed all the data into their optimization models, they got an answer. The absolute best, most precise wall angle they could achieve under the most ideal conditions was this number right here, 29.76 degrees. And just to put that into perspective for you, their target was a perfect 30-degree angle. Getting less than 1/4 of a degree away from perfect, that's an absolutely massive win in the world of precision manufacturing. This is the kind of accuracy that literally changes what is possible. And here it is, the golden recipe. The exact settings to get that near-perfect result with the least amount of effort. It turns out to be a tool speed of about 192 RPM, a really shallow step depth of just 0.1 millimeters, and a feed rate just a little over 1,000 millimeters per minute. So what does this all boil down to? What's the big takeaway? Well, because of this kind of detailed research, we now have a proven, data-backed roadmap for working with one of the most difficult but also most important materials we have. It means we can make custom parts for things like medicine and aerospace that are stronger, lighter, and more complex than ever before. This kind of breakthrough just blows the doors wide open. When you have this level of precision and control over a material this powerful, it really makes you wonder, right? What seemingly impossible part is somebody designing right now? What's going to be the next big innovation built from a perfectly formed piece of a super metal?